Imagine a material with zero energy loss at room temperature. No more frequent phone charging, no power grid waste, and instant tech revolution. But why is this miracle material LK-99 making top scientists argue fiercely? It all started on July 22, 2023, when a South Korean research team dropped a bombshell on an academic platform. They had created the world's first room temperature, ambient pressure superconductor LK-99, a copper-doped apatite crystal. For over a century, superconductors have only worked at ultra-low temperatures or extreme pressures, but they claimed this crystal functioned at 25 degrees Celsius and normal air pressure. Why the sensation? Superconductors carry electricity without resistance, meaning no energy waste. If LK-99 were real, electric cars could fully charge in seconds, power grids would lose no energy during transmission, hospital MRI machines could shrink to the size of a desk, and quantum computers could operate without expensive cooling systems. This is not just a scientific breakthrough, but a complete revolution in daily life. But just as the world celebrated, doubts emerged. The team uploaded to papers within 2.5 hours, and the data inside was contradictory. A physicist from Rice University found that the magnetic data graphs in the two papers came from the same dataset, but the y-axis scale of one was 7,000 times larger than the other, a rookie mistake for a major research. Even more surprisingly, on August 2nd, the team requested retraction, stating that a member had published without permission and the research contained many flaws. What happened next was unprecedented. Laboratories around the world joined the replication effort. Huazhong University of Science and Technology released a video on August 1st showing their synthesized LK-99 crystal partially levitating over a magnet, a key Meissner effect of superconductivity, and netizens erupted again. But just a few days later, Southeast University reported the opposite result. Their sample showed zero resistance at -163 degrees Celsius, but no Meissner effect, and most samples acted more like semiconductors. This is the core of the scientific debate. Superconductors have two unbreakable rules: zero resistance and complete diamagnetism, the Meissner effect that makes materials levitate, and neither can be missing, just like a bird can't fly with one wing. The South Korean team's papers showed only partial levitation and messy resistance data. Huazhong University's sample could levitate but was too small to test for zero resistance. Southeast University's sample had zero resistance but no levitation. Each laboratory only got one piece of the puzzle. Top scientists began taking sides. Supporters said the partial levitation and the team's patent granted in March were signs of legitimacy. Skeptics pointed directly to the messy data and internal divisions within the team. A researcher from the University of Oxford stated plainly, "There is no conclusive evidence of superconductivity, no clear magnetic response, no heat capacity data. Only contradictions." A scholar from Nanjing University was even more direct. "This is most likely an illusion, not a breakthrough." Later, the controversy had a key breakthrough. Researchers from China and Germany discovered that the synthesis process of LK-99 produces a lot of impurities. For every part of pure crystal, there are 17 parts of copper and 5 parts of sulfur byproducts, namely copper sulfide. When heated to 112 degrees Celsius, copper sulfide undergoes a structural phase transition. Its resistance drops sharply, appearing like zero resistance, and it has weak diamagnetism that can cause partial levitation. This is simply a case of misidentifying the material. The difference between the two is subtle but crucial. Superconducting phase transition is a second-order transition, smooth and reversible with no energy lag, while copper sulfide's phase transition is a first-order transition, messy and irreversible, behaving differently when heating and cooling. The German team specially synthesized pure LK-99 crystals without copper sulfide, and what happened? These pure crystals were insulators with a resistance as high as millions of ohms. No zero resistance, no Meissner effect. The mystery seemed solved. But the controversy did not fully end. Some scientists believe that even if pure LK-99 is not a superconductor, copper sulfide impurities may form a composite material with the crystal to produce superconducting properties. Others point out that no laboratory, including the original South Korean team, has been able to fully replicate the superconducting effect. By December 2023, South Korea's National Academy of Sciences released a white paper conclusion. There is currently no evidence that LK-99 is a room-temperature ambient pressure superconductor. Why were top scientists so divided? First, room temperature superconductivity is the holy grail of physics. Whoever conquers it gains fame, funding, and a Nobel Prize with extremely high stakes. Second, scientific progress relies on debate by nature, and the LK-99 controversy shows how science self-corrects. Thousands of researchers test, question, and verify until the truth emerges. Third, the line between breakthrough and mistake is blurred. The South Korean team may not have fabricated data, but only misjudged the results, a common occurrence in cutting-edge research.